All right, so we're approaching exam one now, and it's time to do a little bit of review of what we have already covered and what will be on the exam. First of all, just to remind everyone, I don't think anyone has any doubts about these things already, but just to remind everyone, the exam will be over chapters 6, 7, and 8. We've covered chapter 9, in fact, already, but that won't be on the exam. It'll be 2 hours, 5 to 7 questions, probably 5, though. Most of the exams in the past have been 5. You can have an 8.5 by 11 handwritten cheat sheet, which means you don't have to memorize any of the formulas or any of the facts or any numbers you'd like to know. Standard numbers like conversion factors and the value of KB and the values of R and anything that comes from a thermodynamic table like delta H, delta S, delta G, delta U values, those will all be provided, so you don't have to put those on your cheat sheet. They'll be on the exam. You'll need a calculator, of course, and of course you can't have anything that can make contact with the internet, except, of course, for the computer that you're using in order to get at the exam itself. The exam will be run by Respondus, and it'll be on this coming Monday from 8 to 10 p.m. unless there's further notice. I just assume that's going to be the case. Now, I haven't checked the doodle poll recently, but I'm pretty sure it hasn't changed much. Also, yes, remember that the Respondus exam itself isn't the real exam. It's just the means of proctoring the exam. And so you'll have to upload your exam as a PDF as if it were a homework at the end of the exam. Just finishing out or closing out the Respondus exam itself doesn't do anything. That doesn't actually allow you to answer the questions in any meaningful way. So you have to upload the exam at the end. And it'll be graded by hand. It isn't graded by machine. All right, we've covered 3 major topics: thermodynamics, statistics, and intermolecular interactions. The first 2, of course, are by far the most important ones. The last one was a fairly short section, but we'll talk about that anyway. All these topics are interrelated, especially the thermo and stat mech. I've emphasized that from the beginning, and of course, I think people know what that means. The statistics underpin, I guess is the right word, the second law of thermodynamics especially. So, for the thermodynamics section, it's useful to organize the thermodynamics around the 2 laws, first law and second law. There is a third law, of course, but that isn't nearly as important as the first 2. The first law says, first of all, that we're only interested in equilibrium states. All the other kinds of more complicated things we don't really need to worry about. The thermodynamics describes only equilibrium states, and that's because equilibrium states are the only things that are simple enough to describe with a small number of variables. So remember that 2 plus k variables is enough to completely describe and characterize an equilibrium state. But if it's a non-equilibrium state, then you need a whole lot more variables. So equilibrium states are especially simple. The first law itself, apart from talking about variables, talks about methods of energy transfer. The total change in energy of the system, right? No subscript means it's a system quantity, is equal to the amount of energy transferred as heat plus the amount of energy transferred as work. Those are 2 methods of transfer. The first one is mechanical, whether the work is mechanical, and the heat transfer is basically a diffusion-based process. It's heat diffusion across a boundary. And the reason why those 2 are important, why they're distinct and important, why we worry about this difference at all, is that the heat transfer process is related to entropy. So the heat change is equal to T, the reversible heat change actually is equal, let me put that in there, in fact, that's T dq rev, not just dq, and this is dw rev, that means. So the heat transfer itself is equal to T times ds, and the other terms that appear in the first law as we've been writing it are all different forms of work. There are other terms that I haven't added here. If there were electrical work being done, for example, there'd be more terms. But we haven't talked about those things, and those are much less common than the ones we have talked about, so we will limit ourselves to just PV work, pressure volume work, and then chemical work, which I have mentioned repeatedly but haven't talked about in detail. All right. The PV work that we're talking about is equal to, dW is equal to minus P external dV. Remember, it's the external pressure that matters, not the internal pressure when you're calculating work. If it's a reversible process, those two things are the same, but if it's an irreversible process, then they aren't necessarily the same. And so in that case, it's important to use the external pressure, not the internal pressure. For an ideal gas, for a reversible process that occurs at constant temperature, we derived that the work is equal to minus nRT log V2 over V1. For a constant pressure process, the work is equal to minus P delta V, and again that's P external. And for a constant volume process, well, no volume change means no work, so the work is just equal to 0. Those are the only three cases that we've dealt with. So even though calculating work might be considered to be complicated in general, we've really only dealt with those three cases, so pretty simple in practice. The heat, the most general way of calculating a heat change is to somehow know what the total energy change is and subtract the work. That always works, but relies on being able to get the total energy change somehow. You can't always do that. If there's a temperature change involved, then the heat change is equal to either the CV or the CP times the small heat change dt. And for cases where the heat capacities don't depend on temperature and where there's a finite temperature change, then the heat change is equal to CV or CP, depending on whether it's constant volume or constant pressure, times the temperature change, delta T. For an ideal gas, for constant temperature change, for a reversible process, delta U is equal to 0, and so Q has to equal minus W, and so Q is equal to nRT log V2 over V1. That's just the negative of this work relationship up here. Then for energy and enthalpy changes, for the energy at constant volume is equal to CV delta T. Of course, if you're not at constant volume, then there are other contributions, and so this doesn't work. But if you're not at constant volume, then CV doesn't apply anyway, so this formula always works when it's applicable, when in the right circumstances. If it's a constant pressure process, then the heat capacity gives you the enthalpy change instead of the energy change. Basically, it accounts for work effects that it basically subtracts off work effects so that you just get the heat. Remember also, I didn't write it here, but delta H is equal to the heat change for a constant pressure process. So this is just the heat change. There are a number of Euler relationships. We talked about other ones, those for Gibbs free energy and Helmholtz free energy, and we could talk about the one for entropy as well, though that's easily derived from the one for energy here. But those are all in Chapter 9 or later, and so they're not on this exam. For this exam, the only two Euler relationships that come into play are the ones for energy and enthalpy. These things are very formal and sort of high-level relationships. I don't anticipate that we'll have use for them on this exam, but they're easy enough to put on your cheat sheet, so I suggest doing that. Also, by way of formal relationships, there are all these derivative relationships. Remember, those can be derived or figured out rather quickly, almost by inspection, from the first law. If we look at, for example, the fact that entropy, volume, and mole numbers are the fundamental variables for energy, then temperature, for example, has to equal du ds at constant v and n, and that's one of these derivative relationships down here. So just by looking at the first law, you can get this entire first row of derivative relationships. And looking at the equivalent relationships for enthalpy gives you this second row of derivative relationships. And again, the ones that involve Gibbs free energy, Helmholtz free energy, or entropy are for later, for the next exam. All right, that's a summary, an overview at least of the stuff that pertains to the first law. Now for the second law, remember that the second law, as we've currently formulated it, applies to an isolated system, but then also remember, I mean, it isn't formally on this exam, but we know that the whole universe can be considered to be an isolated system, and so for open systems, we just consider the surroundings to be part of a larger isolated system. So the isolated system, in the end, covers everything. And it says, first of all, the second law says that the entropy has to be a maximum at equilibrium, and vice versa, right? At equilibrium, the entropy is a maximum. So equilibrium and entropy maximum are the same thing. They're interchangeable ways of stating the same thing. If an entropy change is greater than 0, then that change will occur on its own, spontaneously, in the forward direction. If the entropy change is less than 0, then the reverse process will occur spontaneously if there's no outside intervention. And if the entropy change for a small change especially is equal to 0, if there is no entropy change, then you are at equilibrium. And yes, there is this diagram over here that shows what that means diagrammatically. It means, for example, in this particular case, you have an isolated system. I didn't put a thick wall out here, but I should. There's a certain amount of energy on side A over here, a certain amount of energy on side B. There's a temperature difference. Side A is higher in temperature than side B, which means that since we know that the temperature is a driving force for energy transfer, the heat will flow from side A to side B. And we can ask, as heat is flowing, how is the entropy changing? And this diagram gives that. Here's the fraction of energy that's on side A. And at some point, as you're going from high temperature, and the temperatures are starting to equilibrate, of course, they become equal at equilibrium. The entropy initially rises, and then it reaches a point at which further flows of energy won't cause an increase in energy anymore. At that point, the derivative, or the small change in entropy, is equal to 0 for further changes. And going any further than that would actually cause the entropy to go down, and so the process will stop there. Yes, I have mentioned this a couple times already, but all these other new quantities that we have talked about but haven't done much with yet, that's from Chapter 9 and not on this exam. All right, calculating entropy. The most basic relationship is the Boltzmann relationship, S equals KB log W, and that has been useful in a few cases, but we've pretty much exhausted all the cases where that's useful already. It's really hard to use in any practical setting. The thing that's useful in a practical setting is this relationship, ds is equal to dq reversible over T. The fact that it's reversible heat change, though, is important. It means that when you're calculating entropy, you ignore whether the actual process was reversible or irreversible. You always use a reversible process, and that means that you actually use a process that didn't take place in order to calculate the entropy change for the system that did take place. In other words, you pretend that a reversible process occurred. You calculate the entropy using that reversible heat change, and that is, in fact, the true entropy change even for the irreversible process. So dq rev is the heat transferred for a reversible process, starting from the true correct initial state and ending at the true and correct final state. So you have to keep the initial and final states the same, but you invent or construct a reversible process that connects those two, even if it was truly an irreversible process that connected those two. The initial state and the final states always have to be equilibrium states, after all, and there may be non-equilibrium states in between, in the process of getting between those two, but the initial and final states have to be equilibrium states because those are the only kind of states for which any kind of entropy change is even defined. So the initial and final states will always be equilibrium states, but the stuff in between not necessarily. All right, so how do you tell when a process is actually reversible or irreversible? Well, there's a bunch of different tests. Probably the most useful one, the one I usually use, is to look for whether the thermodynamic forces that are causing the change are balanced or unbalanced. In this case, for example, I have a temperature on the inside in my system that's different from the temperature outside. Anytime there's a temperature imbalance like that, that's an unbalanced force, and the process that takes place will be irreversible. A reversible process for the same kind of thing would be the following. You start with the correct temperature for the system, the true temperature for the system, but you imagine that out in the surroundings, instead of having this temperature bath, you have the same temperature, or at least you start with the same temperature as the one that was in the system, plus a small incremental change that allows the outside temperature to change slowly, and slowly it changes to the correct final temperature, which is T2. Right at the end of this process, we'll have T2 on the inside as well as on the outside as heat flows out. And so you have to imagine a process that gets you to T2 on the outside and also therefore T2 on the inside. But what's going on out in the surroundings isn't what really happened. We imagine it happened out in the surroundings so that we can get forces balanced at all points and therefore get a reversible process. And that's the way we calculate the entropy change, but that isn't what actually happened. Yeah, so in the initial temperature is T1 and P1, the final temperature is T2 and P2, whatever that P2 is. I didn't talk about P up here, but there was a pressure, of course. For both cases, both for this true irreversible process and also for this artificial reversible process that we use to calculate the entropy. As far as formulas are concerned, for a constant temperature process, the temperature underneath in the expression for entropy change doesn't change, and so delta S, not just ds, is equal to a finite heat change, reversible heat change divided by temperature. For an ideal gas, for a reversible process that occurs at constant T, Q is equal to minus W, and that's equal to nRT log V2 over V1, as we saw above. Divide that by T, and you get delta S is equal to nR log V2 over V1. Remember, we derived that also using the Boltzmann expression, and therefore showed that at least in this important special case, this expression and our general expression, ds equals dq rev over t, give the same thing. And so that's not a general proof that those two things are the same, but at least it's consistent with that. In general, the delta S change is the integral from state 1, whatever it happens to be, to state 2 of Cv or Cp, depending on whether it's constant volume or constant pressure, of dt over T, and if the heat capacities don't change with temperature, then that's Cv log T2 over T1 or Cp log T2 over T1, depending on what's being held constant. Okay, that's an overview of the thermodynamics to date. Of course, much more is coming in the next section. But we also have introduced into this section quite a lot of statistical mechanics. And remember, the core idea behind statistical mechanics is this distinction between microstates and macrostates. A microstate is one physical quantum state, if you like, or one arrangement of the molecules and their momenta. One particular one. You freeze everything, you see where everything is located, you see how much momentum everything has. That's one microstate. But a macrostate is a whole collection of many of these. You allow now the system to take on many different possible microstates. You gather those up in your mind, at least you gather those up into one big group or set, and you count how many there are in that. Then that's a macro state. That set is a macro state. And this quantity W, the number of elements in the macro state, is of course the important quantity that appears up here when we're talking about the Boltzmann relationship for entropy. So it's closely related to entropy. The number of microstates in the macro state is the entropy of that macro state, or the log of that is the entropy of that macro state. We introduced the ergodic hypothesis, which isn't always true, but almost is always true in all chemical situations is true, which says that all the microstates in the system that have equal energy also will have equal probability. If the system is isolated, that means all the microstates have equal probability, because an isolated system can't change its energy, and therefore all the microstates do have the same energy. And so this ergodic hypothesis applies to every single microstate. But if it's an open system, like we saw when we were talking about the Boltzmann distribution, then all the microstates that have the same energy have the same probability. There are other states with different energies now, because the system can exchange energy with the surroundings, but the microstates that have different energies don't have the same probability. Only the microstates that have same energy also have equal probability. Then, for actually calculating probabilities, for an isolated system, we saw that the probability of one microstate is the number of microstates in that set. And since our set just has one microstate now, that's a 1, divided by the total number of microstates possible. On the other hand, if you're thinking about a larger set of possible microstates, then it's just however many microstates are in that set divided by the total number of microstates. So it's just the fraction of all microstates that are in the set versus the total number of microstates possible. That's, again, a formula we've used a little bit, but again, it's mostly difficult to use. And so much more commonly people use the expression for an open system, or anyway consider an open system. You don't encounter a truly isolated system very often. Almost always your system is open in some way, at least with respect to a temperature bath. In that case, we use the Boltzmann distribution. I didn't put that name here, but let me do that now. And that says that the probability of one microstate is proportional to this exponential factor that has the energy of the microstate in question, divided by or scaled by or in units of this quantity kBt, which is the effective measure of the available energy from the surrounding bath, and then divided by the partition function. We'll talk a little bit down below about that partition function. We've calculated the partition function in a fair number of simple cases, but remember there was always this 0-point energy issue that comes up, and so let's talk about that a little bit more. I haven't talked about this much beforehand, but I thought I'd put it in here, that let's suppose you don't want the probability for just one microstate. Let's suppose you want the probability for a set of microstates that all have the same energy. That's basically the same thing as the probability for a level. I have talked about that using those words. Then it's just the number of microstates in that level, or that have the same energy, whether you consider it to be a level or not. And then times everything else is the same out here, e to the minus u sub I over kBt divided by q. Remember also that this quantity u divided by kBt in microscopic units can also be written as u over RT if everything is in macroscopic units, joules per mole rather than joules. And remember that the quantity RT or kBt, depending on which one you want to use, controls how easy it is for the system to make a transition from a lower energy state up to an upper state, because that represents the amount of energy, or how easy it is to extract energy from the surroundings. If the temperature is low, there isn't very much available energy in the surroundings. It gets very hard to find the energy necessary to make this transition. If the temperature is high, there's a lot of energy in the surroundings. It gets easy to make the transition. And then what that means, of course, is that there's very little probability in the upper state for this low temperature case, and nearly equal energies in the upper and lower states for this high temperature case. All right, let's come to this 0-point energy term. I haven't actually systematically explained this in the past, and I'm not sure it's how helpful it is to say something about it at this point, but let me just do so anyway. The partition function is always given by the sum of all these exponential factors, with each energy in turn appearing as you sum over all the possible energy states. And if the energy of the ground state is not 0, then this first term isn't necessarily a 1, but I can always factor out an exponential from all the other terms. So that's what I've done here. I've taken this first term and factored it out, and that means that the second term, the second term and the third term and higher order terms become energy differences, right? This is delta U1 and this is delta U2. It's the difference in energy from the ground state. So it's this energy, it's the energy difference from the ground state that appears in the exponential factors rather than the absolute energy U1 or U2. And that means that you can write the partition function as a ground state 0-point energy factor times a partition function with the energy at the ground state taken to be 0. And we'll call that Q ZPE equals 0, so a little subscript that says that the 0-point energy is taken to be 0 in this case. And that's the sum of all the energy differences. All this is just a formal way of doing what I've been doing sort of informally in the examples up to now. And let's see how that works. Well, if these relationships up here are correct, then the probability from the Boltzmann distribution can be rewritten by factoring out the 0-point energy, the energy of the ground state, on the top in this factor, and also on the bottom in the partition function factor. And then they divide out, and only the energy differences matter. And this is a general example of the fact that absolute energies never matter in any physical setting. It's always only energy differences or energy gradients that cause forces or changes or have effects in any physical setting. So that's also true when you're talking about probability. It's true when you're talking about mechanical forces and motions and stuff, but it's also true when you're talking about probability. Only energy differences affect the probability, and that means you're always free to choose the 0 of energy to be at the lowest energy state, and that's usually the convenient choice, as long as you then use energy differences from the ground state in calculating the Boltzmann distribution, or calculating the partition function specifically. Yeah, and I think this all just says the same things, except to point out that this quantity, the partition function for which ZPE is equal to 0, is the thing for which counts the number of effective states available to the system. If you have this 0-point energy factor in here, then Q's interpretation is more problematic or more difficult. So it's really Q ZPE that's the fundamental quantity, even though I haven't emphasized that before this. All right, that's a little overview at least of the statistical mechanics. Finally, let's talk about the intermolecular interactions. This was a short section and a pretty definite section, right? Just a set of formulas, really. So let's go through them. We're talking about the interactions between atoms, essentially. There's bonding interactions, and there's also down here non-bonding interactions. Among the bonding interactions, there are, let's see, 1, 2, 3, 4 different kinds. There's the Morse potential, which gives the full curve, the full bonding curve between two atoms, and has the form energy is equal to a quantity D times 1 minus e to the a r minus r0, all that quantity squared. The shape of that function looks like this as a function of r, the intermolecular distance between two atoms. The quantity d is the depth of the well, right? If r goes to infinity, then this quantity goes to a certain value, and d tells you how high that value is compared to the minimum of the potential. R0 gives you the value at the minimum, and the quantity a tells you how sharp this minimum is. For a small, it's a broad minimum. For a large, it's a sharp minimum. And so those three parameters, D, A, and R0 control the shape of the Morse potential. Morse potential is widely used as a sort of phenomenological approximate way to describe the bonding characteristics between two atoms in practical calculations. If I'm not worried about actually breaking a bond, I'm just worried about stretching the bond a little bit, if I'm worried about vibrations basically, then I can approximate the energy of interaction between two atoms with a harmonic potential, which is 1/2 a force constant times r minus r0 squared, just two parameters now, the force constant itself and the position of the minimum, r0. The bigger this force constant is, the stiffer or narrower this interaction potential is, and the smaller it is, the broader it is, so it's a lot, plays the same role anyway. It's not the same quantity at all, but plays the same role as this quantity A in the Morse potential. I think that's enough about that. I can say more. There's lots more to say about this. Harmonic potentials are tremendously important, mainly because they're simple in a huge variety of situations, but that'll do for our purposes, present purposes. If you are talking about a bond bending rather than a bond stretching, situation, then there's also a harmonic potential for in the angle between three different atoms, right? So in the bonding bend angle between three atoms, and that's got a force constant and also an equilibrium or minimum angle now. There's a theta 0 where the angle prefers to be, that's the minimum of the potential for, theta 0 there. That's the minimum of the potential for a bending interaction. And then finally, the last interaction, bonding interaction, is the dihedral energy. That also has a force constant. It has a multiplicity factor. It's usually 3. In all the examples we've used, it's been 3. And then an offset. We've always set that offset to 0 in all the examples, but it doesn't have to be 0. It can be. So it's got 3 parameters. And if you plot and it depends on this angle chi, which is the dihedral angle, of rotation around a bond that connects 4 atoms together, rotating this end of the arrangement relative to that end of the arrangement. And because of clashes between the two ends, that energy is high when the ends are in a staggered arrangement and low when they're in an eclipsed arrangement, and that staggered and eclipsed arrangement repeats as you go around at 360 degrees, and hence you get this. That's what this multiplicity factor is accounting for, right? If that n were 4, that would mean that there would have to be 4 substituents here, not just 3. And yeah, that's right. And so anyway, it looks like that. The value of it's got the same symbol as a force constant, but it isn't really a force constant. The value of this kappa chi quantity is the depth of these cosine wave bumps in the dihedral energy. All right, I think that's clear enough. Then there are the non-bonding interactions. There's really only 2 of those. There's the charge-charge interaction, and there's the induced dipole interaction, or the Leonard-Jones potential, and the Coulomb potential. We've seen that the Coulomb potential can be conveniently written to give you kilojoules per mole out when you put electrons in for charge and angstroms in for distance. And don't forget the dielectric constant quantity in there. There isn't too much to say. I think we practiced using this a little bit. I guess a few qualitative things. First of all, if both charges are plus or if both charges are minus, then the interaction is repulsive. The atoms will be forced apart by the charge-charge interaction. But if they're of opposite sign in either direction, either pair, then it's attractive and the atoms will be pulled together by the interaction. If the system is in water, the dielectric constant basically accounts for the effects of the environment that surrounds the charged particles. If you're in water, dielectric constant is very large, it's about 80. If you're in some other environment like protein, well, the dielectric constant varies, in fact, in that case, but it tends to be around 4. If you're in something that's even more hydrophobic, like the interior of a lipid membrane, then it's even smaller, about 2. And if there is no medium surrounding you, or if the medium is air, which is basically the same as vacuum, then the dielectric constant is 1, and then there is no effect of dielectric constant at all. Notice that given where the dielectric constant is here in the formula, the more hydrophilic or more polar, really, the environment is, the weaker the Coulomb interaction or charge-charge interaction is. So it's much weaker. It's 80 times weaker in water than it would be in air. And it's weaker even in protein than it would be in air, and even in lipid than it would be in air. But notice that it also means that if you take 2 charges out of water, and put those same charges inside of a protein, that the interaction gets much stronger because the dielectric constant has gone way down. It's gone down by a factor of 20. Here, this interaction is 20 times stronger than this interaction would be in water. All right. The other through-space interaction, or non-bonding interaction, is the induced dipole interaction. We talked about the physical origin of that. An atom is polarizable. It can gain a dipole moment. And that can happen just by accident. So there are fluctuating dipole moments occurring all the time in every atom. Once a dipole is created in one atom, it creates an electric field that induces a dipole in nearby atoms. And statistically, that tends to be a dipole that's arranged in a way that's favorable, that interacts favorably with the original dipole. And so you get a net interaction between even neutral atoms just due to these fluctuating dipoles. The fluctuating dipoles tend to be statistically correlated in ways that makes them attract each other. That interaction, the induced dipole, really it's just this term that's the induced dipole part. This other term here is accounting for repulsions between the atoms when they start to actually bump into each other. That's the hardcore repulsion between 2 atoms that says that two atoms don't want to overlap with each other. And so really this second term here is the only induced dipole, the only part that's really induced dipole. But anyway, we call this whole thing the induced dipole interaction, just for short. And it's called the Lennard-Jones potential. It has a 1 over r to the 12th term, a 1 over r to the 6th term. If you plot it as a function of r, you get something that looks, in fact, a fair amount like the Morse potential. It isn't exactly the same as the Morse potential, but qualitatively it is. It has 2 parameters, this quantity epsilon, which gives how deep the well is, and this quantity big R, which tells you where the minimum in the well is. The Lennard-Jones potential is always attractive, at least when you're far enough out, and that's usually what we assume, that the atoms are far enough away so that they're not actually on this repulsive part of the curve. The induced dipole part, in fact, is always attractive. It's this atom-atom bumping into each other part that's repulsive. So it is actually true that the induced dipole part itself, which is just this second term here, is always attractive. All atoms have it. It's universal. It's fairly weak, but there's a lot of these interactions, so collectively they have a big effect. The value of epsilon tends to be around 1 kilojoule per mole. There's quite a wide range in that number, though, so it can be much smaller or much larger. And the value of the minimum position tends to be maybe even a little bit bigger than that. 2 to 4 angstroms, I think, is probably a little bit better. Actually, yeah, 2 is probably a little bit short. 2 and 4 is probably a little bit long. So anyway, that's probably a pretty good idea for what the total range is. And I think that is the end of this review. So good luck on the exam.